Definitely, that is smudge here, so it's, as a matter of fact, examining fundamentally the earliest structures we know in the universe. This sort of information arrives in a small part of the time that we were previously aware of. So, I think a parcel of the records that we have in the current-day universe are going to be broken actually soon. A notable Nobel Prize victor says that the James Webb Space Telescope has recently found something odd in the universe, and the progressions that are coming may not even be prepared as far as we're concerned. The latest discoveries are exceptionally bad for science. To an ever-increasing extent, insane things are happening. Since James Webb has viewed a shiny new impact, it is turning our physics books on their heads. Adam Reese, a space expert and Nobel Prize victor, has long thought that science is nearly at catastrophe. There are heaps of perplexing issues that are getting greater consistently. As indicated by specialists, could we at any point still sort out what's happening? Or is the area of science over? Adam Reese is likely one of a handful of the specialists who are trying to keep mentally collected nowadays. Things are not equivalent to they were before the James Webb Space Telescope was sent off. It's logical that the universe is a lot more seasoned than we suspected. Systems have formed a lot quicker and in completely different ways than we suspected they would, and the universe may not be developing from a single point. What would it be a good idea for us to do now if dark matter was only a mix-up? James Webb is already showing us the following image of abnormal things occurring in the universe. Quite possibly one of the most learned individuals in the space of concentrating on how the universe is extending is Adam Reese. His work on finding that the universe is growing faster than we thought meaningfully impacted the manner in which we contemplate the universe and was a major piece of the Hubble energy. Since he has worked hard for quite a long time, Reese knows that our comprehension of the universe is off base, so he is amped up about what the telescope has found. As of late, he made a difference by taking a gander at the universe and utilizing supernovae as standard candles. Interestingly, researchers utilize astronomical scales to measure how far things move and how fast they move. Standard lights are a lot like those using supernovae as standard estimations, which were incredibly precise. Yet, there was as yet one issue. Reese and his group found that the universe was extending in certain areas more than others, which was not what they thought would occur. During their work, something else turned out to be clear. Reese's estimations were completely different from those based on the redshift method, which shouldn't have been the case. The Hubble tension is what we currently call these differences in the estimations. Their work was so impressive that Reese, along with his colleagues Saul Perlmutter and Brian Schmidt, won the Nobel Prize in Physics in 2011. It just so happens, he won the honor for tracking down that the universe is growing faster than previously thought. Schmidt and Reese are both part of the High Z Supernova Search Team, which is looking into ways of further improving how far things can be measured in the universe as a feature of the Supernova Cosmology Project. Perlmutter, on the other hand, came to the same outcomes around the same time. They saw type Ia supernovae, which are very brilliant stars that detonate and are a good method for determining the distance away things are in the universe. These discoveries shocked everybody by showing that the pace of expansion of the universe is going up rather than down, as was thought before due to the gravitational pull of matter in the universe. The isotropic universe was an impractical notion. It was growing to be the most serious issue in modern science, and now it's happening. Nowadays, researchers and cosmologists are continuously being given new inquiries and stunning realities. Now, the thought of an isotropic universe is also going to fall apart, taking with it one of the main pieces of our understanding of the universe. Regardless of what way you look at the universe, isotropy says it looks the same. A key piece of the cosmological principle says that if we examine the universe on a large enough scale, it is uniform and has the same regions. For example, the pattern of cosmic microwave background radiation appears to be similar everywhere. Likewise, large groups of galaxies are spread out evenly in space, or at least that's how it looked in the past. Researchers transformed these observations into simple mathematical rules to make it easier to explain the world, but this might have been a mistake. Adam Reese and other researchers studying accelerated expansion first demonstrated the isotropic model to some degree because measurements of supernovae had shown that the pace of development is consistently the same. That's all there is to it. It seems as though there is some sort of isotropy. However, the development is happening much faster than old physical theories suggest it should. The end of dark energy science is still very intriguing right now. Now we need to find out more about dark energy to solve the new cosmology puzzle. We still don't understand what this energy is made of, but knowing that it exists and what it does is significant for understanding how and why the universe grows in a way that isn't slanted and how the current standard model of cosmology came to be. Dark energy is thought to be a type of energy that could exist anywhere in the universe. It is possibly a vital piece of the current hypothesis about how the universe is growing. It is believed to be the force pushing against gravity and accelerating the expansion of the universe. According to the ongoing cosmological model, dark energy makes up around 68% of all the energy in the universe. There is already an issue here. Researchers say that an energy that has never been proven to exist is responsible for nearly 70% of the energy processes in the universe. The observation of type Ia supernovae by Adam Reese and his colleagues was a key part of the case for the existence and properties of dark energy. Until recently, the rapid expansion seen here couldn't be explained without a strong force pushing against it. The cosmic microwave background radiation and other large-scale structural investigations have shown that this mysterious energy is real. However, new discoveries made by the James Webb Space Telescope, JWST, have made people question the idea of dark energy. The JWST can observe the early universe with more precision than was possible before. The standard model of cosmology says that structures and objects should be younger and less developed than they were when the first detailed observations were made. It's possible that these findings show that the universe may have started earlier or expanded much faster than previously thought. Before these discoveries, it was believed that we fully understood some significant cosmic components and forces, like dark matter and dark energy. This could mean that the conventional model of the universe needs to be completely reevaluated. That's not something we're ready for yet, but we can't come up with new hypotheses until we know more about what's going on. Will the universe of particles hold the answer? We'll have to wait a little longer for the change in how we see the world. We won't be able to build a new picture until JWST sends us more images and researchers discover even more astonishing things. Could take a while. For now, specialists all over the world are searching for solutions that are entirely new. David Gross, another researcher, sees this as an opportunity. Gross says that the answers to the universe's big questions aren't hidden in the big picture but in the small picture. A notable theoretical physicist who knows a lot about string theory and strong forces, he is also a Nobel Prize winner. In 2004, he won the prize for discovering asymptotic freedom in the theory of strong interactions. The finding was essential for learning about how quarks behave. Quarks are the building blocks of protons and neutrons. Gross believes that our understanding of the universe must start with the smallest components of matter. The quantum world, where particles interact in strange and unpredictable ways, may hold the key to solving the mysteries of dark energy and the universe's expansion. He argues that understanding the fundamental forces and particles could provide insight into how the universe behaves on the largest scales. String theory, one of the most ambitious ideas in theoretical physics, offers a potential framework for unifying the forces of nature. According to this theory, the fundamental building blocks of the universe are not point-like particles but tiny vibrating strings. The vibrations of these strings determine the properties of particles, such as mass and charge. While string theory remains unproven, it offers a tantalizing possibility, a way to bridge the gap between quantum mechanics and general relativity. The challenge lies in testing these theories. The energies required to probe the quantum structure of spacetime are far beyond what current particle accelerators can achieve. However, indirect evidence, such as the behavior of black holes or the structure of the early universe, might provide clues. Gross and other researchers are hopeful that advances in observational technology, like the JWST, will bring us closer to these answers. Meanwhile, the discovery of anomalies in the universe's expansion has sparked debates among cosmologists. Some propose that dark energy may not be a constant force but something that evolves over time. This idea, known as dynamic dark energy or quintessence, suggests that the properties of dark energy could change as the universe ages. If true, this would fundamentally alter our understanding of cosmology and require a revision of the standard model. Others argue that our assumptions about the universe's isotropy may be flawed. If the universe is not perfectly uniform on the largest scales, it could explain some of the discrepancies observed in cosmic data. This idea challenges the cosmological principle and suggests that the universe may have a preferred direction or structure that we have yet to uncover. The implications of these discoveries extend beyond cosmology. They touch on fundamental questions about the nature of reality, the origins of the universe, and the ultimate fate of everything. If dark energy continues to dominate, the universe will keep expanding at an accelerating rate, eventually reaching a state known as the Big Freeze, where galaxies drift apart, stars burn out, and all matter approaches absolute zero. On the other hand, if dark energy behaves unpredictably or reverses its effects, the universe could face a big crunch, collapsing back into a singularity. Alternatively, a balance between dark energy and gravity might allow the universe to reach a steady state, avoiding either extreme. The search for answers is a testament to humanity's curiosity and resilience. Despite the challenges, researchers remain optimistic that breakthroughs are on the horizon. The JWST and other advanced observatories are just the beginning of a new era in astronomy, one that promises to reshape our understanding of the cosmos. As we gaze deeper into the universe, we are reminded of how much we have yet to learn. Each discovery brings us closer to unraveling the mysteries of existence, but it also reveals new questions. The journey to understand the universe is endless, but it is a journey worth taking.